With today's modern printers, those of us in the US and other 120 volt countries are at a slight disadvantage over you guys in the 240 volt countries. Now, that wasn't always the case. Hey guys, this is Justin Nelson's Projects. If you're new here, I do projects on everything from 3D printing, electronics, microcontrollers, hell, plumbing, automotive, you name it. If it's a project, I film it, I make a video out of it. Now, I'm a little behind on some of the other stuff because I've been focusing mostly on 3D printing lately, but I'm getting to all that, I promise. I am a little ADD, so we'll see. But in the meantime, if you like that kind of stuff, if you like random projects of all sorts, hit that subscribe below. If you like this video by the end, make sure to give it a thumbs up. And now back to Whiteboard Justin. Older printers had a little switch on the back near the power socket to switch it between 120 and 240. And they don't do this anymore. Now, I have figured out why that is the case, but it took a little while. I brainstormed a lot of it and I put some of it into action, which I'll show here in a little bit. But first, those older printers, what did that switch do exactly? Well, I'm going to show you, so let's zoom in on the whiteboard and get to the math here. I promise it's really simple. So I'm going to use a selfie stick as a pointer because it's what I had lying around and I don't want my arm getting in the way of the whole shot here. But we all know Ohm's law, V over R equals I, and that can be twisted around in all different variations. For the purposes of this, we are assuming that this is a purely resistive load because that's what a heater is. It's a purely resistive load. So we don't have to worry about reactance, inductance, any kind of phase relationships, any of that. You treat it just like you would with DC. So to simplify this argument for our purposes, voltage divided by resistance times voltage gives us our wattage, because V divided by R gives us our current in amps, and then the amps times the voltage gives us our wattage. So the way the older printers worked, the way my monoprice printer is wired, these numbers aren't right for the monoprice printer, but we're going with the numbers that would equate to a modern printer. So let's say the modern printer had two elements and a switch. That switch wires the two elements either in series or in parallel. If you're in a 240 volt country, it would wire them in series. And if you're in a 120 country, it would wire them in parallel. Again, the monoprice printer and a lot of other printers, if it had a 120/240 switch on the back, that's what that switch was for. In a 240 volt country, this is wired in series. So these are 30 ohms a piece. In series, 2R is 60 ohms. So using this simplified formula, 240 divided by 60, 4 amps. 4 amps times 240 volts gives us 960 watts. So 240 divided by 60 times 240, 960. Now let's go to the US or any other 120 volt country and flip that little switch. Now these are wired in parallel. So 30 ohms and 30 ohms in parallel gives you R over 2 gives you 15 ohms. 120 divided by 15 gives us 8 amps. So we've got half the voltage but a quarter the resistance. So you end up with 8 amps. So you got double the amperage, but you got half the voltage. So 8 times 120 still gives you 960 watts. So 120 divided by 15 times 120, 960. So no matter where in the world you live, you just flip that little switch telling it if you're 120 or 240. Future Justin here with a kind of simpler explanation. If you look at the series wired 240 volt version, effectively you've got a voltage divider there. So across each of those individual heating elements, you can measure 120 volts. Whereas when they're wired in parallel and running at 120 volts, once again, you would measure 120 volts across those 30 ohm resistors. Okay, so back to the rest of the explanation. Now, modern printer, single element heat bed, no switch to flip. So if you happen to live in a 240 volt country with outlets that look like that, well, 240 divided by 60 equals 4 amps. Times 240, 960 watts, same as up here. But if you live over here, 120 volts divided by 60 ohms gives us only 2 amps. So we got half the amps, we also have half the voltage. And that means we have a quarter of the wattage, 240 in this case. I chose 60 ohms to make the math easier, but this is pretty close to what is stated on the data sheets for these printers. Now the printers are usually rated at 1100 watts max in a 240 country and 350 max in a 120 volt country. Where's that extra 100 watts coming from? Well, that's our 24 volt PSU that runs the rest of the printer. It may use up to 100 watts, so they include that in the maximum rated. So if we take away that 100 watts for the rest of the printer and only focus on the print bed, you are getting 4 times the wattage, 4 times the heat, and basically a quarter of the time to heat that bed as us here in the US. So my thinking was this: we actually do have 240 volts available here in the United States. Most residential homes are fed with a split phase power system. Our neutral is in the center, and then you have 2 hot legs 180 degrees out of phase with each other. So 120 volts, 0, 120 volts. If you take from leg to leg, you get 240 volts. Now also, commercial buildings are a lot of times wired in 3-phase, and in that case, going from one leg to another leg gives you 208, but from one leg to neutral still gives you 120. I'm not gonna get into the math on that. That's way beyond my pay grade here today. For argument's sake, let's say you're setting up your print farm, you've got to rewire and add circuits anyway. Why not go 240 or 208, whichever is available in the building you're setting up in? And by the way, 208 gives you 721 watts. Still a pretty respectable bump from the 240. So why not do this? Well, number one, what I learned was the advantages of doing this only apply while heating the bed from ambient up to temperature. The rest of the print, everything else is the same. It doesn't really reduce your print time much in any other situation. Reason number 2 we don't do this: if we wire it this way in the US, what we're feeding as the neutral to the printer is actually one of the 120 volt legs, and then the hot is the other 120 volt leg, which means our earth ground is 120 volts away from what it thinks is neutral. And that goes against all the NEC regulations, so that's kind of out. Whether it's 208 or 240 doesn't matter. Your neutral can't be that far away from your earth ground. Now, they're very much isolated. It's not like the earth and the neutral come into contact or are wired together in any way in the machine, but it's still supposed to be at the same relative potential. So that's out. Then I got to thinking, what about a transformer? I just happen to have, okay, obviously I'm not gonna hook a microwave transformer, but what if we went on Amazon and picked up a step-up transformer that can handle at least 1,000 watts? And if you've got multiple printers set up, you would need multiple 240 circuits just for that few seconds at the beginning of a print. It's not worth rewiring. It's certainly not worth the expense of a step-up transformer, but I tried it anyway. So of course I did have to buy a step-up transformer and do a few experiments. And what I found was that lights were blinking. Every time that heat bed kicked on, the lights would flicker in the room. And running it through my UPS, which is 120 volts, so it had to run before the transformer. Every time that heat bed kicked in, UPS actually beeped on me, let me know it was overloading. And it's a 1000 VA UPS. Oh, my UPS is beeping. Yeah, it's beeping. That's interesting. The UPS is pretty much at its limit. That was just a warning. I was right at the tippy top of the limit. Notice that voltage, by the way, out of the transformer dropped to 230. Holy crap, that is so much faster. That was the fastest I've ever seen it heat that bed up. And once it actually shut down on me. So that's when I just said, okay, this isn't gonna work. Now, obviously I could have bought a 240 volt UPS, a bigger transformer, or done the kind of sketchy wiring trick I was thinking about, but in the end, we don't typically have appliances that plug in and use 1,000 watts on demand whenever the hell they want. Aside from the kitchen, of course. Obviously, the kitchen is generally wired with more branches at 20 amps for your microwave, your coffee maker, your kettle, whatever. For the rest of the house, we generally don't have appliances just deciding, hey, I need 1,100 watts for a few seconds to heat this thing up. That's just not a thing around here. So we are at a disadvantage, but it's only for a few extra seconds. I timed it. It's maybe 2 minutes per print. It's not a real big deal. Not worth all of what I put into testing this. Definitely not worth rewiring your home in an unsafe manner. So definitely don't try it. But hey, it was a thought experiment. I just had to try it. Well, that's really all I've got for you today. If you like this kind of video, I do projects of all sorts. YouTube thinks you might like this video up here, but real quick, head down there and hit that subscribe so you don't miss out on further content, and maybe give this a thumbs up if you liked it. Leave some comments, and we'll discuss. Thanks for watching.